it is acceptable to have power come in via breaker and out via the MLO terminals. This is a common configuration for shore power connections on vessels. The breaker provides overcurrent protection for the incoming power, while the MLO terminals are used to connect the shore power to the vessel's electrical system. The pair of shore power breakers alone cannot serve as overcurrent protection for the transformer primary. The primary overcurrent protection must be located at the transformer itself. The shore power breakers are only intended to protect the incoming power from overcurrents and not the transformer. Let's delve into the specifics of applying these concepts in a marine environment, particularly when dealing with shore power connections and transformers. When modifying a vessel's electrical system to accommodate a change in shore power voltage, such as from 240 volts to 480 volts, several crucial considerations come into play. Firstly, the configuration of the new panel board is critical. Using a 480-volt MLO panel board with two breakers, one for the shore power receptacle and conductors on the forward end and the other for the aft end, is a reasonable approach for providing a disconnecting means. The mechanical interlock preventing both breakers from being closed simultaneously adds an extra layer of safety, preventing potential overloading or conflicting power sources. However, the fact that the vessel has no 480-volt loads and the 12 unused slots in the panel board seem purposeless highlights the need for a transformer to step down the voltage to the existing 240-volt system. Connecting the panel's MLO termination points to conductors that serve the primary of a 480 volts to 240 volts transformer is a typical solution. Now, let's address the key questions regarding this setup. The use of breakers for incoming power and MLO terminals for outgoing connections is indeed a common and acceptable practice. The incoming breakers serve the vital role of protecting the system from overcurrents originating from the shore power source. They act as a first line of defense, preventing excessive current from damaging the vessel's electrical equipment. The MLO terminals then provide a convenient and safe way to distribute the power to the transformer. However, it's absolutely crucial to understand that these shore power breakers, sized to protect the incoming shore power conductors, cannot be relied upon as the sole source of overcurrent protection for the transformer primary. This is where the NEC, National Electrical Code, provides clear guidance, even though it may not be strictly applicable in this marine setting. The NEC mandates that transformers must have overcurrent protection on both the primary and secondary sides to safeguard against faults and overloads. The primary overcurrent protection is specifically intended to protect the transformer itself from internal faults or excessive current draw on the secondary side. Therefore, a dedicated overcurrent protection device, such as a circuit breaker or fuses, must be installed at or near the transformer primary. This device should be sized appropriately based on the transformer's primary current rating and in accordance with applicable standards, such as NEC Table 450.3. This table dictates the maximum allowable overcurrent protection for transformers based on their voltage and impedance. For example, if the transformer has a primary current rated of 20 amps, the overcurrent protection device should typically be sized at no more than 125% of that value, or 25 amps. This ensures that the transformer is adequately protected without nuisance tripping under normal operating conditions. Furthermore, the secondary side of the transformer also requires overcurrent protection, typically provided by a circuit breaker in the main switchboard. This breaker protects the secondary conductors and the loads connected to them. The size of this breaker should be based on the transformer's secondary current rating and the ampacity of the secondary conductors. In the context of the provided scenario, where each of the two breakers on the new panel is rated at less than 100% of the transformer's primary current rating, it's even more critical to have a separate overcurrent protection device at the transformer primary. Relying solely on the shore power breakers would leave the transformer vulnerable to damage from overloads or faults. The location of the transformer primary overcurrent protection is also important. Ideally, it should be located as close as possible to the transformer terminals to minimize the length of unprotected conductors. This reduces the risk of a fault occurring in the conductors between the transformer and the overcurrent protection device. In some cases, the overcurrent protection device may be integrated into the transformer itself, such as with a thermally protected transformer. However, in most cases, an external circuit breaker or fuses will be required. When selecting the overcurrent protection device, it's also important to consider the interrupting rating. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without failing. The interrupting rating must be greater than the available fault current at the transformer primary. The available fault current can be calculated based on the utility source impedance and the transformer's impedance. If the interrupting rating of the overcurrent protection device is too low, it could fail to interrupt a fault current, leading to equipment damage or personal injury. In addition to overcurrent protection, it's also important to consider grounding and bonding requirements. The transformer must be properly grounded to provide a low impedance path for fault currents to return to the source. This helps to ensure that overcurrent protection devices will operate quickly and effectively in the event of a fault. Bonding refers to the connection of all non-current carrying metal parts to the grounding system. This helps to equalize the potential between different metal parts, reducing the risk of electric shock. In a marine environment, grounding and bonding are particularly important due to the presence of salt water, which is a good conductor of electricity. Proper grounding and bonding can help to prevent corrosion and stray current problems. When installing the transformer, it's also important to follow the manufacturer's instructions and all applicable codes and standards. This will help to ensure that the transformer is installed safely and correctly. Some common mistakes to avoid include using undersized conductors, failing to provide adequate ventilation, and neglecting to properly torque connections. Undersized conductors can overheat and cause a fire. Adequate ventilation is necessary to prevent the transformer from overheating. Properly torquing connections is essential to ensure that they're tight and secure. In summary, when modifying a vessel's electrical system to accommodate a change in shore power voltage, it's important to carefully consider the overcurrent protection requirements for the transformer. The shore power breakers are not sufficient to protect the transformer primary. A separate overcurrent protection device must be installed at or near the transformer primary. This device should be sized appropriately based on the transformer's primary current rating and the available fault current. Additionally, proper grounding and bonding are essential for safety. Always follow the manufacturer's instructions and all applicable codes and standards when installing electrical equipment. Now let's elaborate further on selecting the appropriate overcurrent protection for the transformer primary, since it's a critical aspect of ensuring a safe and reliable electrical system. The selection process involves several key steps, each requiring careful consideration. Firstly, you need to determine the transformer's primary current rating. This information is typically found on the transformer's nameplate, which is a metal plate attached to the transformer that provides essential technical specifications. The nameplate will list the primary voltage, secondary voltage, kilovolt ampere or kVA rating, and the primary and secondary current ratings. The primary current rating represents the maximum current that the transformer is designed to handle on its primary side under normal operating conditions. Secondly, you must select the type of overcurrent protection device. The two most common types are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent or short circuit occurs. They can be reset after tripping, making them a convenient option for many applications. Fuses, on the other hand, are sacrificial devices that melt and break the circuit when an overcurrent occurs. They must be replaced after they blow. Both circuit breakers and fuses have their advantages and disadvantages. Circuit breakers are generally more expensive than fuses, but they offer the convenience of being resettable. Fuses are less expensive, but they require replacement after they blow. Circuit breakers also offer more precise overcurrent protection, as they can be calibrated to trip at specific current levels. Fuses, on the other hand, have a fixed current rating. Thirdly, calculate the maximum allowable overcurrent protection. Once you have the transformer's primary current rating, You can calculate the maximum allowable overcurrent protection using the guidelines provided in the NEC, specifically Table 450.3. This table specifies the maximum allowable overcurrent protection for transformers based on their voltage and impedance. As mentioned earlier, for transformers with a primary current rating of 9 amps or more, the overcurrent protection device should typically be sized at no more than 125% of the primary current rating. For transformers with a primary current rating of less than 9 amps, the overcurrent protection device can be sized at up to 167% of the primary current rating. However, it's important to note that these are just maximum values. In some cases, it may be necessary to use a smaller overcurrent protection device to provide better protection for the transformer. Fourthly, consider the available fault current. The available fault current is the maximum amount of current that could flow in the event of a short circuit. This value depends on the utility source impedance and the transformer's impedance. The utility can provide the source impedance information. The transformer impedance is typically expressed as a percentage on the transformer nameplate. You can use this information to calculate the available fault current using the following formula: fault current equals transformer kVA times 1000 divided by the square root of 3 divided by the voltage divided by the transformer impedance. It's crucial to select an overcurrent protection device with an interrupting rating that is greater than the available fault current. If the interrupting rating is too low, the device could fail to interrupt the fault current, leading to equipment damage or personal injury. Fifthly, select the overcurrent protection device with the appropriate interrupting rating. Once you have calculated the available fault current, you can select an overcurrent protection device with an interrupting rating that is greater than that value. Circuit breakers and fuses are available with various interrupting ratings. The interrupting rating is typically expressed in amps. It's important to choose a device with an interrupting rating that is high enough to safely interrupt any potential fault currents. Sixthly, coordinate the overcurrent protection devices. In some cases, it may be necessary to coordinate the overcurrent protection devices on the primary and secondary sides of the transformer. Coordination means selecting the devices so that the overcurrent protection device closest to the fault will trip first, isolating the fault and preventing unnecessary outages. Coordination can be achieved by selecting devices with different time current characteristics. Time current characteristics describe how long it takes a device to trip at different current levels. By selecting devices with different time current characteristics, you can ensure that the device closest to the fault will trip first. Seventhly, install and test the overcurrent protection device. Once you have selected the appropriate overcurrent protection device, it's important to install it correctly and test it to ensure that it is working properly. The installation should be performed by a qualified electrician in accordance with all applicable codes and standards. After the installation, the device should be tested to verify that it trips at the correct current level and that it has the appropriate interrupting rating. In addition to these steps, it's also important to consider the environmental conditions in which the transformer and overcurrent protection device will be operating. In a marine environment, the equipment will be exposed to saltwater, humidity, and vibration. It's important to select equipment that is designed to withstand these conditions. For example, circuit breakers and fuses should be enclosed in weatherproof enclosures to protect them from saltwater and humidity. Connections should be made with corrosion-resistant materials. Remember that selecting the appropriate overcurrent protection for a transformer is a critical task that requires careful consideration. By following these steps, you can ensure that your transformer is adequately protected from overcurrents and short circuits, and that your electrical system is safe and reliable. Furthermore, always consult with a qualified electrical engineer or electrician for specific guidance on selecting overcurrent protection devices for your application. They can help you to determine the appropriate device size, interrupting rating, and time current characteristics based on your specific needs and the characteristics of your electrical system. Remember, safety should always be the top priority when working with electricity.